Okay, let's delve into the signature process and take a look at the first thing. The first thing is there's a command line. This is included in the source code I'm giving you that is in Sig Test. And Sig Test is a command line tool for just running and verifying some signatures and taking a look at how the code works. What you want to be able to do is test the reading of a key file, make certain that that part works, make certain that you understand how a signature gets signed, and then make certain how it gets validated. So this code is here for you to play around with and test the signatures. Inside the Sig Test directory in assignment 5, there is a makefile. The makefile has some things in it. We should be able to run this Sig Test that you see. I'm going to highlight it right here. And I'm going to run that with make, but basically it's going to take that signature file that starts with 6E11. I have no clue what the password is for it, so I'm just going to type something in and make certain you cannot sign without having a correct password. We'll get back to looking at the code inside this in just a minute, but make sign 1. And I don't know the password, so I'm just going to type in a couple random characters, and yes, it just gives me back an error. Let's try make sign 2, okay, which is it's going to prompt and say this is the password so that I know what to type in. I'm not going to try to type that in. I'm going to cut and paste it. It produces a signature. It's interesting to save this signature and look at how long it is. But here's the message that it's signing, which is some sort of a hash of some piece of data or something that I've put in. It's some string on the end of the command. And here is the actual signature. So if we cut and paste that signature, and we just stick that in a file, let's just make a temporary file, we can see how long that signature is. And turns out to be 131 characters. I suspect one of those characters is an end-of-line character. So 130 divided by 2 is 65 bytes of data. And that's taking that each byte is one octet pair or hex pair. So it should come out to 65. Some things to observe in this is that would be two 32-byte pieces, the X and Y coordinates in our encryption system. And remember I said that there's a V value that is either 0 or 1, and you'll see at the very end, there's the V value in hex, in this case a 1, which is the most probable value for that V as in the quadrant in which those X and Y are in. So there's what a signature looks like, there's what a message looks like. Now this is valuable information when it comes time to actually getting this to work. Let's see if we can validate. Let's do verify 1. And part of the validation is making certain that if you send an incorrect signature, it doesn't validate. That seems to work. And verify 2. And it says that, yeah, for this signature, it recovered, and it has recovered, yes, a public key. And information that is this. And here is the address of the account, which is your EIP55 format coming from that public key. And that should match with the address that we sent in up here. And it does. So yeah, we have a match and a successful account. So this piece of code, whatever it is, runs to produce the correct results for signing and verifying. Now we've got a bunch of pieces that we've got to put this all together in, but all the code is in here to do this. So let's look at what the code is. And there are other pieces in here. This is a complete command line key generation management set of stuff. But you look at something like this and change passphrase. I bet that reads in a key file and allows you to update your password on that. Check PW, probably. Well, what would you want to do with one of these key files? You'd want to find out if you know the correct password. There's a couple files there. Generate probably generates a key file. Inspect, that probably allows you to go into a key file and get information. What kind of information? It's an encrypted file. So the information you want to get is somewhere in inspect. It tells you how to open up a key file, probably prompts for a password, and then pulls out the two pieces of information you want is the public key and the private key. So there's those, a library, a main, message test, run test, sign message. Sign message, I bet that does a signature on a message. Some utilities, probably should be in the library file instead, but whatever the utilities are, and a verify message. So let's take a look at how you sign a message. And you'll notice that there's a copyright notice that this came right out of Ethereum, because we're using the same key system that they are, and some sort of a help message up the top as to how you run it. You always hope that those things are actually correct, but you don't know for sure. And it does some sort of command line flags. And it has action sign message. Looking at this, I go, okay, does a bunch of stuff, and down here, after it's run some things, it prints some stuff out. So there's some print stuff down here with a flag, and up here it has some command line processing. But you get to looking at this, and clearly that's the piece that does the work. Okay, so let's go to that location in the file. Okay, and in VI I can just hit a star, and oh, it's right here in this file. Okay, so here's the actual piece that does the work to generate a signature. So we've got 3 input parameters, a key file, a password, and an in message. And it has output parameters, a message and a signature or an error. So it reads the key file. Okay, if it can't read the key file, you get back an error. That seems to make sense. If you decrypt the key file, if it gets an error from that, yep, it passes back an error. We saw that error earlier in this section of video. It says if the length of the message is 0, then it generates a random 20-byte message. Okay. I'm not certain what the utility of that is, but certainly the person who wrote it probably had a reason for doing it that way. Of course, if you just want to check that you're getting a correct signature and you just pass in an empty message, it just generates some message. Okay, that kind of makes sense. And it takes the message and it encodes it hex to string. I bet if you did a printout after that, you'd find that whatever your characters are now hex digits. And then it calls crypto sign. You sign the hash of the message, okay, and you sign it with the private key. The private key came from us reading in the decrypted key up here. That seems to make sense to me, since what you do is you sign with a private key, checks errors again, and then it encodes the result of that raw signature from up here into a hex, and it returns stuff with a nil for success on the error. Okay, so, you walk through that and look at it and you go, okay, this looks like pretty much what I would do to generate a signature. Either for the homework, you copy this and you're going to tweak it a little bit, or you copy the whole function and you call it. But this looks like the process that you need. Let's take a look at verify. Verify message. Again, a copyright notice. Obviously, it was pulled from Ethereum. Again, we hope that this actually is a good help message. The first thing I see is this says Sig Test, and when I compile it, or it says Key Test, and when I compiled it, it was Sig Test. So obviously, they haven't updated the message quite right, but I can live with the name of the command being wrong. And it seems to be laid out the same sort of way, where we've got an action verify message, okay, which does some command line processing that I don't quite understand yet. But in the middle, it's got, yeah, there's a function. And looking at the print statements afterwards, if it failed to verify. We saw this message once when we ran things. If the signature verified, it prints that out, and it prints out the public key. We saw those messages too. So the code we're interested in is this verify signature. And let's go, I bet it's in this file. This is a nice way to lay it out. They did command line processing, and then they built a function that did the work. So here we go. Verify signature takes an address, a signature, and a message. The address has to be the account address. That was the thing that had it was the big hex number in the key file, and it's also the number of the address of an account. So an address, a signature, and a message. And it assumes the message is in hex because it immediately decodes the message. Then it checks some common library function. Is hex address? Okay, so it verifies that that address is an address, which probably means to me that it's checking that it's the right size, that it's hex digits, and that it is EIP 55 formatted. So you probably just can't send in an address. It has to have the correct format. Then it converts that address to some internal data structure. It decodes the signature. Again, it's a hex, and it's expecting to get it back into some sort of a buffer of data. And then here's the call into the cryptographic stuff to do signature to public. So it takes the signature and the message, and it gets back a recovered public key. Okay, I can live with that. The recovered public key, then it uses something, encode to string. Oh, okay. It takes the cryptographic ECSA public key and it converts that into a recovered public key. All right. I'm a little bit lost looking at this code, but I'm kind of following it. And then public key to address. So it takes the public key, because remember, addresses are a piece of a public key. A public key is 32 bytes, and an address, I think, is 20 bytes out of that. And it converts it, and then it checks to make certain that the address here is the same as the raw address here. So at the end, it checks that your signature produced the correct address. And that's when it says that if it didn't, if the addresses don't match, it's not a valid key. And then it returns your recovered address. Okay, so there's some kind of mystery things here that we'd have to go poking into this section. If we really want to understand it, we'd have to go poke into that section and go look at those and read the comments and figure it out. But the bottom line of it is that we send some things in, and at the end, we're looking to compare addresses and see if they match. And we've got to do some tweak stuff to get from public keys to addresses, but the code is there. And if that's the test. So now we know how we validate, even though we may not know the details of some stuff in the middle. That we'd have to go find those things and poke into them. There's also some mystery. This one here is a mystery. If I wanted to understand it thoroughly, I would go find where the library common is. It's in Ethereum, and go see what the comment is or what the process is on is hex address. But I'm guessing it checks that it's EIP 55. So we've got some code that we kind of walk through that shows us how signatures get signed and how they get validated. It makes a bunch of library calls. Note-wise, I'd take some notes down that to really get a good handle on this, I got to go poke into some of the Ethereum code and take a look at it. But implementation-wise, if I was in a hurry, I wouldn't go poke into it. I would assume we've got a piece of code, it works, let's just use it and see what happens, because it kind of has it packaged together. And it appears to have a couple little mistakes like key test in it. I could maybe fix that. In fact, I probably will fix that before you see this and update it here.